All right, a very, very warm welcome to today's webinar where we will deep dive into the world of statistical inference together with two doctors of statistics who have completed their doctoral thesis on partly this subject of inference. So we are with us Stina Zetterström and Alessandro Mastrototaro. There we go.
Thank you.
Very warm welcome, both of you. We will first start with hearing from Stina for about half an hour. Then we'll switch over to Alessandro for another half hour, and then we'll dedicate the final half hour to a discussion and questions from you in the audience. Excellent. And with that, I will hand over to Stina.
Thank you. I will share my screen, see if it works. So thank you for inviting me for this webinar. Today I will talk about work I did during my PhD at Uppsala University. And the talk is called Bounds for Selection Bias in Causal Inference. And it was also the title of my thesis. And the work I will present today was done with my supervisor, Ingeborg Wernbaum. And part of it was also done in collaboration with Arvid Sjölander at Karolinska Institute. So the target in many studies is to estimate the causal effect of a treatment variable on an outcome. And observational studies are an option when randomized trials are not applicable, for example, due to ethical or financial reasons. However, among other types of biases, selection bias can occur in observational studies. And selection bias can arise, for example, from missing data or dropouts in a study, but it can also arise when the study population is constructed, which is often by a series of inclusion or exclusion criteria. And in applied work, one way to present this selection is usually in a section called something like data and study population. And this is just an example from a paper in British Medical Journal from a few years ago that looks at adverse pregnancy outcomes and heart problems. And here I have marked in blue the selections that they make. So first, they only include singleton births in the study. And they also exclude women with a previous heart condition and women with some missing information. And in this part, quite a lot of the original population is kept, but there are other examples where the population is reduced quite a lot. And this is such an example. So another way to present this selection is in this sort of selection diagram, where you can start with the total population on top. And here, the figure on the right is a zoomed-in version. You can see that it's almost 94,000 people, and then through a series of selection, that is decreased to 3,800 something. And this is usually it, and these selections are not considered that much more. So what we are interested in is bounding a possible bias from these types of selections. And today I will talk about 5 different bounds. The SV bound was presented by Smith and Vanderwill in a paper from 2019, and that we have investigated in more detail. And the other 4 bounds, the assumption-free and GAF and so on, are presented and derived by us. And the reason that several different bounds might be useful is that they all depend on different assumptions and rely on different amounts of information and different sensitivity parameters. So one bound that is valid in one situation might not be valid in another, and thus it's good to have options. And this is the outline of the rest of my presentation. So I'll begin by describing the model, some notation, and define selection bias. And then I will first go through the SV bound shortly, and then present some properties of the SV bound that we have investigated. And I'll present the sharp bound that is similar to SV bound, but can be used as an alternative. And then go through a different set of bounds called the assumption-free bounds. And then I will end with a short description of our R package and end with an empirical example. So we start with some notation. So we assume that we have a binary treatment variable A and binary potential outcomes YA, where Y1 denotes the outcome a subject would have if it had received the treatment, and Y0 denotes the outcome the subject would have if it received the control. We also assume that we have a binary selection variable S, and this can be constructed from several inclusion or exclusion criteria. We also assume that we have a vector of unmeasured variables U, which I will talk more about shortly, and lastly a vector of observed pretreatment covariates X. We also have to make some assumptions, and the first is consistency, and that is that the observed outcome is equal to the potential outcome under the received treatment. So if a subject receives the treatment 1, then the observed outcome is equal to Y1. And if a subject receives the control, then the observed outcome is equal to Y0. We also assume conditional exchangeability in the total population, but not in the selected subset of the population. We also assume that all analysis is done conditional on the pretreatment covariates. So to make the notation a bit simpler, we will remove X from all the formulas and equations, but implicitly X is conditioned on throughout the work. And lastly, we ignore sampling variability, which means that the observed means are treated as an approximation of the corresponding asymptotic mean. And before moving into more details, I want to talk a little bit about the term selection bias, as it is kind of ambiguous. So first of all, many special cases of selection bias have been given their own name, either from the person first presenting it or from the problematic situation. And examples are Bergson's bias, healthy worker bias, follow-up bias, survival bias, attrition bias, and so on. And it's quite common to use these names instead of selection bias when actually selection bias is the problem. Secondly, when the term selection bias is used, it is not consistently done so. And sometimes the term selection bias is used to describe a bias when it is not possible to estimate a valid causal effect within a selected subpopulation. So it's a problem of internal validity. And that would be the right part of this figure here. So we have a selected population that is of interest from which you have a sample, and you find an effect estimate, but that is not an unbiased estimate of the true causal effect. And in this figure on the right here, it would be that you have the study population, which is the group of pink people, and even when you are only interested in that, you can have bias estimating the causal effect. In other instances, the term selection bias is used to describe a bias when it's not possible to generalize an estimated causal effect from a subpopulation to a larger target population. So it's external validity that is a problem. And that is then the left part of this figure here. So even if you have estimated the causal effect in the selected population without any bias, that causal effect is not the same as the causal effect in a larger target population. And you cannot generalize the conclusions. And in the figure on the right here, it means that the causal effect for the pink people are not the same as the causal effect for the pink, green, and blue people, which are interested in. However, recent works try to make things clearer and define selection bias more careful. And one suggestion by Liu et al. From 2022 is to use the terms type 1 and type 2 selection bias. And type 1 selection bias refers to the problem with internal validity. So the right part of this figure, or the problem with the pink group in this figure. And type 2 selection bias then refers to the problem with the external validity. So the left part of this figure, or the problem with this arrow here in the figure on the right. And the methods that I will talk about today applies to the risk ratio and risk difference in both these target populations, but in this presentation I will focus on the causal risk ratio in the selected subpopulation defined like this. So we are concerned with bias within the pink group. So this CRR is the effect we wish to estimate, but what we observe is this risk ratio here. And selection bias is defined as a ratio of the risk ratio, so the observed risk ratio divided by the causal risk ratio. And this is not the usual definition of bias, and the reason that we use this one instead is that we are interested in investigating conditions when the observed risk ratio is not a causal effect, rather than investigating properties of an estimator of the observed risk ratio. And now I will move on to talk about the bounds. So the first bound that I looked at is the SV bound. And as I said, that was proposed by Smith and Vanderwill in a paper from 2019. And they bound the causal risk ratio like this. And the interpretation is that the causal risk ratio is at most shifted to this value in the presence of selection bias. One requirement for the SV bound to be valid is that there exists an unmeasured variable u, or a vector of unmeasured variables u, such that a conditional independence assumption is fulfilled. And for the subpopulation, it's this assumption, which is a kind of conditional exchangeability assumption for the selected subpopulation. And the reason for using this assumption is that if we could observe u, which we cannot, then it would be possible to estimate the causal effect without any selection bias. If instead the interest lies in the total population, a slightly different version of this assumption is needed. And the SV bounds for the causal risk ratio in the subpopulation are defined like this. So the lower bound is the observed risk ratio divided by this bounding factor. And the upper bound is the observed risk ratio multiplied by another bounding factor. And the bounding factor looks like this, where these RR parameters are kind of risk ratios. And these sensitivity parameters, they describe the strength between the unmeasured variable and the outcome treatment and selection variable. They all include this unmeasured variable u, which means that they are unknown and must be guessed. And the question then is which values should be considered. And we wanted to try to answer this question. So first, the user must provide values on these unknown sensitivity parameters. But if values that are not logically possible are used, it means that the bounds are not valid. So only values of the sensitivity parameters that lie within their feasible regions should be considered. And the sensitivity parameters can be restricted by their functional form, by each other, or by the observed data. And by functional form, I mean that these sensitivity parameters are ratios of probabilities. So without doing any more work, at least we know that they must be greater than 0. And we found that the sensitivity parameters are all restricted by their definitions to values equal to or greater than 1. And we also found that they're all variation independent of each other and of the observed data. And this means that that all values of the sensitivity parameters above or equal to 1 are possible, although not equally plausible. And that the value of one sensitivity parameter and the data does not need to be taken into account when considering another sensitivity parameter. So when the user can consider the values of these sensitivity parameters before actually observing the data and can consider them all separately. Another property that we were interested in was sharpness of the SV bound. And a bound is sharp if the bias can actually be equal to the value of the bound for an observed distribution and correctly specified sensitivity parameters. And we found that the upper and lower SV bounds for the risk ratio in the subpopulation are sharp if certain conditions are met. And that is that the underlying assumptions are fulfilled, and that the sensitivity parameters and distribution fulfill this inequality here, so that the bounding factor is smaller than or equal to 1 over this probability with the outcome. And so if these two are fulfilled, then the SV bounds are sharp, which only means that it is possible for the bias to be as large as the bound, not that it necessarily is as large. So what happens if this inequality is not fulfilled, so that the bounding factor is greater than this ratio? Well, then the bounds are still valid, and they can be used to bound the bias, but they are too conservative. So you know that the bias will never be as large as the bounds suggest. And the question we asked then was if we can improve on this. And the short answer is yes, we can. So we used the same sensitivity parameters as the SV bounds, and we also included some observed data to derive improved bounds. And we define LA like this and UA like this. And LA and UA are then bounds for this potential outcome probability. And L1 and U0 and U0 and L0 can then be combined to obtain bounds for the causal risk ratio. And it's basically this term here that is the difference from the SV bound. So instead of just including the bounding factor, we have the minimum of the bounding factor and the sharp limit. And we have the following properties of these sharp bounds. So first, the bounds LA and UA are valid, which means that these inequalities hold for all distributions. Secondly, L1 and U0 are simultaneously sharp, which means that there exists a distribution such that this potential outcome probability is equal to L1 and this potential outcome probability is equal to U0. Again, it doesn't mean that the bias is necessarily that large, just that it is possible. And thirdly, we have the opposite, so the bounds L0 and U1 are simultaneously sharp. And the sharp bounds and the SV bounds will coincide in the region where the SV bound is sharp, but outside of that region, these alternative bounds are tighter. So now I have talked about the SV bound and the sharp bounds, and they are very similar, and they rely on the same conditional independence assumption and use the same sensitivity parameters, but the sharp bounds include some more data. So now I will talk about this second set of bounds. So they instead rely on this decomposition of potential outcome probability. So this probability here can be decomposed like this. And the probabilities that are marked in blue are observed from the data. And it's only this counterfactual probability marked in red that is unobserved. So if we can find bounds for this counterfactual probability, then we can find a bound for the potential outcome probability and in turn for the causal risk ratio. And there are two options. The first is to set this counterfactual probability equal to 0 for a minimum bound for the potential outcome probability, and set it equal to 1 for a maximum bound. And this is what we have done in the assumption-free or the AF bound. However, the AF bound tend to be quite wide and usually are relatively uninformative. So another alternative is to try to bound it in some way. And this is what we're doing in the generalized AF and counterfactual AF bounds. And I will start by describing the GAF bounds. So if we have this unmeasured variable u according to this conditional independence assumption, the same as for the SV and sharp bound, then this implies that the counterfactual probability is bounded by these two unobserved probabilities. And they both include the unmeasured variable u, so they are unobserved, but they are probabilities for the observed outcome instead of this counterfactual probability. So if we use these probabilities as sensitivity parameters and insert them into this decomposition of the potential outcome probability, then we can get a lower and upper bound for the causal risk ratio. And the lower bound is defined like this, and the upper bound is defined like this. And the difference is that for the lower bound, lowercase ms is in the numerator and uppercase ms is in the denominator. And for the upper bound, they have switched places. And the GAF bounds are equal to the assumption-free bounds when the sensitivity parameters are set to their most extreme values. And that is why we have named this bound as we have, as it is not actually assumption-free, but it shows the connection between this bound and the assumption-free bound. We also investigated some properties of the GAF bound. And we start with the feasible regions. And first, the sensitivity parameters are probabilities, which means that they must be restricted by 0 and 1. Secondly, here we also have that from construction that they are restricted by the observed data. So lowercase ms lies between 0 and this observed probability, and uppercase ms lies between this observed probability and 1. So the user, if the user wants to calculate these bounds, then he or she must observe the data first. We also have that the GAF bounds always cover the null effect. So that is for the risk ratio, the lower bound is always below 1 and the upper bound is always above 1. And this might look strange, but these bounds are not the same as confidence intervals. And in some scenarios, it might be clear which direction the selection bias occurs in, and only one direction of the bound would be of interest. We also looked at sharpness and found that the GAF bounds are not sharp. And the definition of sharpness was that it is possible that the bias is equal to the bound for an observed data and correctly specified sensitivity parameters. And here it is not possible to get the sensitivity parameters equal to this counterfactual probability without making assumptions that at least one variable has a point distribution, which would then violate the conditional independence assumption that includes the unmeasured variable u. And this is also a reason for why the GAF bound covers the null effect. Since it is not sharp, it would be possible to construct a tighter bound, and then this might not be the case anymore. So the GAF bounds rely on this conditional independence assumption, as I just said, as do the SV and sharp bound. That means that if this assumption is not fulfilled, neither of these bounds can be used. And this could, for example, be if the selection is influenced directly by the treatment and the outcome. And one alternative is to use the assumption-free bound. But as I said, these tend to be quite wide and might not be that informative. So an alternative is to use the counterfactual probabilities directly in the bound and use these alternative sensitivity parameters. And again, the counterfactual AF bounds are equal to the AF bounds when the sensitivity parameters are set to their most extreme values. And here, the feasible regions of the sensitivity parameters are that they lie between 0 and 1, and that uppercase ms star is greater than lowercase ms star. So these are not restricted by the data. And also the CAF bounds do not necessarily cover the null effect. They still can, but they don't have to. And we also found that the CAF bounds are sharp. And this is since they are equal to the causal estimates when the correct value of the sensitivity parameter is used. So that was the theoretical part of the presentation, and now I will shortly present this R package selection bias and end with the empirical example. So the bounds that I have presented here are compiled into an R package to facilitate for the end users. And currently version 2.1.0 is available on CRAN. And this R package includes functions to calculate the bounds from sensitivity parameters or from a data generating process and data when that is necessary. And it also includes a simulated data set for users to test the different functions. And in some more detail, the package includes these functions. So the first is sensitivity parameters M. So the user here specifies a data generating process according to the M structure, and the package calculates these sensitivity parameters, either for the SVR sharp bound or for the GIF bound. It also includes functions to calculate all the bounds that I have presented here, either from the output from this function or from users specified values of the sensitivity parameters and the necessary data. It also includes a function that checks if the SV bound is sharp or not. And lastly, this simulated dataset Zika-learner, which is inspired by an empirical example from the Smith and Vanderbilt paper, which looks at the causal effect of Zika virus on microcephaly in babies. So if the mother has Zika virus, what is the risk of the baby having microcephaly? And it is simulated according to this structure. Okay, the empirical example. So the sharp bounds are demonstrated by investigating the effect of breakfast eating on overweight, which is dichotomized as BMI greater than 25, using the NHANES data from 1999 to 2018. And marital status might be considered to be a proxy variable for other variables that may be correlated with breakfast eating and overweight that are more difficult to quantify. For example, socioeconomic status and lifestyle habits. So you might think that marital status is a confounder and that you have this structure. However, it could also be that marital status is not a confounder, but is a collider from these two other variables, V and U. And conditioning on it would then not decrease the bias, but actually introduce selection bias. And in this data set, the observed risk ratio is 0.97. So eating breakfast slightly decreased the risk of overweight for men who are married or living together with someone. And the question then is, have the selection on men who are married or living together with someone introduced bias for that subgroup? And in this figure here, it's a contour plot for the upper sharp bounds for different values of the sensitivity parameters. So this bottom curve here, the lowest curve, that is where the causal risk ratio is actually equal to 1. So there is no no effect. And then the upper bounds, the curves that lie over that is that the causal risk ratio increase. And we see that even for quite small values of the sensitivity parameters, so here they are roughly 1.3, the relationship is actually reversed. So if you might think that you are in the scenario on the right and marital status is not a confounder but a collider, then you might be careful in the interpretations. So to conclude, study population inclusion or exclusion criteria can result in selection bias, and sensitivity analysis can help to assess the magnitude of this bias. And one way is to calculate bounds. And here we have looked at different bounds and derived others. And we found that the SV bounds are only sharp under certain conditions on its sensitivity parameters and data. And we have derived an alternative sharp bound based on the same sensitivity parameters. And we have also presented alternative bounds based on unknown probabilities. And all bounds that are presented here are available in the R package selection bias. And here are the main references. And thank you very much for listening.
Excellent. Thank you very, very much, Stina, for that in-depth presentation on bounds and biases. Very, very interesting. We'll get back to you with questions a bit further on. So thank you once again, and I welcome Alessandro back.
Thank you.
Thank you very much for having me. It's really nice to talk again about my PhD thesis, which I associate to a nice period of my life at KTH. So I will talk about advances in sequential Monte Carlo-based statistical learning, online algorithmic and variational inference, which is the title of the PhD thesis under the supervision of Jimmy Olson. Okay, so I will start with some introduction and background, and then after this I will actually go through the 4 papers that compose the thesis and try to make it flow and connect them together. So first of all, I will start by defining the problem motivating the thesis, so which is statistical inference, or in special case when we have online data, so data that is received regularly in time, such as GPS signals, returns on financial assets, epidemics, also video frames, and then we want to construct a mathematical model to process this data and make inference on that. And we want to do it in an online fashion. But when we say online, what does it mean? And in the thesis, I've identified these 3 main points. So we want a constant computational effort. So we don't want with time to have to reprocess more and more data. We want constant memory requirements so that we don't want to run out of memory as the data sequence increases, and then we want long-term stability. This is a bit more technical, but simply we want to have still a reliable inference even after several hundreds or thousands or millions of iterations and data points. So I will start by giving a brief overview of state space models, also called hidden Markov models, for the ones who don't know them. But basically they consist of a bivariate Markov chain where we have a hidden process, which is denoted by the variable x, which is simply a Markov process. And then we have partial observations of this process, which are conditionally independent given the latent process. And we only observe the process y, but we don't observe the process x. And then we have also, you can see here, like we have Markov transition densities for the hidden process indicated by the notation m, and Markov transition process for the emission process, or for the observations generating process that is denoted by g. And both of these are also, they have this subscript theta, which is a parameter which can be known or unknown. Now it's not yet important. We will come back to that later. And some examples are linear Gaussian models, which are typically benchmarks because we typically can do exact inference on those. And then other classes like speech recognitions, which is the first motivating problem for introducing historically hidden Markov models. And then we have stochastic volatility, which is a model used in finance when target tracking, when we are having signals from a moving target and we want to reconstruct its trajectory. And now let's go through a few quantities that we will deal with from now on. So we have the complete data likelihood. So assuming that we have also observations from the latent process, then we can define with the complete data likelihood simply the likelihood of all the data that we have, even the data observed and the data that is unobserved. And if we integrate the complete data likelihood with respect to x, we have the marginal likelihood, which is the likelihood of the observed data. And then we have the smoothing distribution, which is the conditional distribution of the latent process given the observed process. And then the filter distribution, which simply is the conditional distribution of the current state. Let's say that we are at time t of the current state, latent state, given all the observations up to the current time. And the problem is that the marginal likelihood involves an integral in high dimensions and typically intractable, unless in a few specific cases, which are the linear Gaussian state space model, or when the state space of the latent process is finite. And since this marginal likelihood is also involved in the smoothing and the filter distribution, then these become are hard to determine exactly. So my thesis deals with sequential Monte Carlo. I'll try to tell it what for the ones who don't know it, tell what it is in a nutshell. So we assume that we have some particles and weights that are an important sampling that are a sample that can be used like in importance sampling to estimate expectations with respect to, let's say, the smoothing distribution. So we have capital N particles and weights. So each particle is basically a sample trajectory of our process, and the weight is just a non-negative quantity given the importance of that particle. And then by taking the weighted average of some functional h, some functional of the trajectory evaluated in each of the particles, by taking the sample average, we can approximate the expectations with respect to the smoothing distribution. And this, and also there are results such as consistency, central limit theorems, and so on. But the sequential Monte Carlo, so far, this is basically importance sampling, but sequential Monte Carlo gives us the tool that as soon as we receive a new observation, y+1, then we can update our sample according to this algorithm. This algorithm has basically 3 main steps, I would say. So the first one is the selection or resampling. So we use, this case, multinomial resampling. So we draw with replacement indices proportionally to the weights, and then we propagate the particles associated to those indices to obtain a new state for the trajectory. And this is the mutation step, line 3, which is where we use like a Markov transition density, or in general, like an instrumental distribution that is of our own design. And then we attach the new sample to the trajectory. And then we have to update also the weights. And then this is basically, it's basically a random Nikodym derivative accounting for the discrepancy between our target distribution and our instrumental distribution. And as I said, there is this selection step that is important, this resampling, because otherwise if we would simply have to do a mutation and then multiply the new weight, this quantity, by the old weight, and with this subsequent resampling, we would end up into a degeneracy phenomenon where just one sample will have a weight dominating all the others, and so basically a one sample approximation, completely useless. And then another thing that I've mentioned is that we can design this Markov this instrumental distribution conditional on the current particle we should design it. And then a common choice is to use the bootstrap, which simply we propagate according to the latent distribution. Otherwise, we have the locally optimal. Before saying that, once you may see from here that the weight in this case these two would simplify with the bootstrap choice, so we would only have the G, so the emission density to evaluate, so this weight would not depend on the current state. And then we have the locally optimal, which instead takes into account also the new observation to propagate the particle. But the problem is that this integral at the denominator is typically infeasible, so we don't have an exact definition for R in this case, and so this is typically feasible only when in the linear Gaussian cases again, so that are typically the ideal scenario. And here I can show you, I hope it works. Yes, I created this GIF of a visual representation of a SMC algorithm. So we have the particles at time 0, and then some of them get resampled and then get propagated at time 1. But the weighting here, this is basically the weight function. And so only the ones with close to the mode of the weight function tend to get resampled multiple times. And the ones that are in kind of brown beige are the trajectories that are somehow killed, because only a few selected particles are typically resampled multiple times and then are propagated. And you can see from this GIF that the more the time passes, the more the blue lines here reduce, because it's by resampling, then we just create a sort of an ancestral line, and in the end all the particles actually will have a common ancestor, which is what we are saying here. And this is an issue. I don't know, maybe also from genetics you might know that there is this concept of the most recent common ancestor, and there is a paper where this has been studied in the case of sequential Monte Carlo, where you can see that they say simply that the number of generation back in time for until when we find a common ancestor is of the same order of the number of particles. So here you can say I've been quite lucky with these simulations, because actually after 20 iterations we have the common ancestor at time 0. So, but if you proceed with the same SMC algorithm, we say that all the particles here after 50 iteration have a common ancestor at time 32, so which is 18 back in time, and then after 500 it's at 489, so which is 11 back in time. And the issue here is that maybe for filtering problems where we are only interested at the current state, the support is diverse, but when we want to compute smoothing distribution, then we basically have particles that share in large part they share the same trajectory, and this is a problem again, because we're basically representing the diversity of our sample is compromised. So the overview of the papers, I will go briefly through those. So the first one is on algorithmic inference. So we focus in the sense that we focus on Bayesian state inference in SMC algorithm, and we evaluate the accuracy. We will see soon what this means. And the issue that I've just presented about particle path degeneracy will be the main motivation for those two papers. And then we switch to variational inference. So where the focus then becomes parameter estimations and the design of the proposal distribution of the distribution RT that we have defined earlier in the SMC algorithm. So the first paper, it's called Fast and Numerically Stable Particle Based on Line Additive Smoothing, the Adasmooth algorithm. So joined with my supervisor, Jimmy Olson, and his former PhD student, Johan Allenlöf. So our goal here is to do compute smoothing distribution. So like expectation with respect to smoothing distribution, in the sense that we have a functional of the trajectory. In this case, the functional can be written in this nice form where it's an additive function over time. And this is typically, this has application in frequentist and Bayesian parameter estimation techniques, such as recursive maximum likelihood, because it involves like the score function of the complete data likelihood. So it's not our arbitrary choice, but it has a reason why this is an interesting problem. And we define these tau quantities that are simply the functional evaluated in the trajectory up to time t of each particle. And then these tau can be easily updated with the following recursive update. So we just, after having resampled in the particle filter, we just take the statistic tau associated to the resampled index, and then evaluate the additive part evaluated in the resampled particle and in the propagated particle. And this is a really nice, it makes the algorithm fast with constant memory requirement, because we don't need to store the whole trajectory, which that would cause an explosion of our memory, but we can just simply save these quantities at every step. The issue here is that due to the particle path degeneracy that we have introduced earlier, then we have a quadratic variance, growth of the variance. And so this is a problem. And that's why we instead introduced the AdaSmooth algorithm, where in addition to considering the resampled particle, we also do this operation called backward sampling, where we kind of draw an index from the earlier generation proportionally to this quantity, which, loosely speaking, tells like how likely a particle at the previous generation could be the parent particle of the current one. I can show it more like with this example. In addition to that, we do adaptive resampling, and so we resample only when it's needed. So when a certain measure of the skewness of the weights, like the effective sample size, is below a certain threshold. And also we do this operation also adaptively, in the sense that we do it only when the number of trajectories are too low, below some certain threshold. So let's say that here at iteration 3, we have the first resampling. We see that the number of distinct trajectories now becomes 6. And then we have another resampling. We still have 6 trajectories. And then here, our trajectories go to 4. So what do we do here? Okay, we say, okay, in addition to the resampling, we also do some backward sampling. So each new particle is linked to another particle sampled according to point 1. So each of them will be linked to 2 particles, so to the true parent and to another one that is likely to be a parent, loosely speaking. And then we take the average of the updates that we would have in case we would proceed forward from one or the other. And then we proceed, and from here we can forget about the past, because these statistics are combining together trajectories. So like it's like a new generation is starting here. And then we can proceed again, like we are beginning a new ancestry line of 10 distinct particles. And then again, we have some resampling, and then the same process can be repeated multiple times. So even if here there are only 2 trajectories left, this doesn't matter anymore, because they get recombined together, and this stabilizes the algorithm. And we have proofs in terms of consistency, asymptotic normality, and also, which is the most important, the stability of the method. And here you can see some numerical results. Here in particular, it's a lot of information, I understand, but this is like the time normalized box plots through time. So we have 3 different time steps, 300, 600, and 900. So the poor man is actually the naive algorithm that had quadratic growth of the variance, and you can see that this box plot through time increases. But the Ada-smooth, which is the first 4 box plots, are typically constant over time, even if with different parameterizations that indicate how the thresholds of this adaptive resampling and backward sampling. And these two are the 2 current methods in the literature that are much slower than the Ada-smooth. And in some cases, we are also able to reduce the variance compared to these 2. Then we proceed to paper B. I'm going a bit slow, I apologize for that. But so this paper B instead deals with filtering expectations. So we moved from smoothing to filtering, so expectations with respect to the filtering distribution, so only considering the last state of the trajectory. And a well-known result is a central limit theorem, which is expressed by this claim. And this is important because the central limit theorem also would allow to construct confidence bounds. But the problem is that we don't know how to estimate the asymptotic variance. And actually, we would know. One way is to do it, okay, we run several independent particle filters, and then we compute the same sample variance scaled by the number of particles, and then we would have it. But of course, we would like to do something in that we don't need to have additional simulations, but just use the particles that are already given by the particle filter. So here we can see that there is this formula actually that we can use without additional simulation to compute an estimate of the asymptotic variance, sigma t, and which is, we will define this sigma t0 t of f. So f is any functional of the state. And this formula, what is basically saying, so first we compute a sum over the set of subtrees starting at a certain time. So let's say that at time 0 we only have a subtree because the resampling, as we said, we have a common ancestor eventually. But let's say that if t0 is time 6, then we have 2 subtrees. So you can see 1 here and 1 here. And then we compute the deviations from the particle filter estimate, which is this quantity. And then we sum over, we square this quantity. So we basically, if we want to see it more in another way, so this is the variance between among subtrees. So it's basically computing the variance among subtrees at a certain time. But then, like, how do we choose this time 0? Because there should be a right way to choose this time 0 and to compute an estimator that approximates correctly this asymptotic variance. Well, there is the first suggestion given from 2 articles from Chanel Lai and Liam Whiteley, suggested to use the time 0. So we always consider the beginning of our algorithm. And this is consistent as n goes to infinity, but the issue is that, as we all know, that there is the particle path degeneracy now, and this means that there is only 1 subtree, so we are basically computing a variance of 1 element, and this variance then it's 0. Then Olson and Duke in 2019, they suggested, okay, let's consider always a certain, we just go back in time of a fixed amount of iterations. So we don't go to 0, but let's say we always go back of 10, 20 generations, and then let's consider the subtrees 20 generations back in time. This introduces bias, but they also prove that this bias decreases geometrically fast with the lag. So actually, even with relatively small values of this lag lambda of times back in time, we would be able to to have low bias. The issue is how to automate the choice of this lambda, because we don't know in advance what could be good. We have to the classical bias variance trade-off. So low lag, we have low variance but high bias, and high lag, we have high variance and low bias. So the Alvar estimator, which is our contribution, is instead automating the choice of this lambda by simply using this concept that a shorter lag should have a higher bias and should underestimate the variance. But if it's giving a higher estimate than the one than a larger lag, then it's probably more stable and better than the one that we would choose. It's a bit tricky, like, to understand the logic, but the important thing is that we have proven that this is consistent as n goes to infinity, and also we have heuristic arguments that actually, on average, the lag chosen at every iteration will stabilize at a value which is proportional to the logarithm of n, where n is the number of particles, giving us a total complexity of n log n. So the complexity does not explode by evaluating also all these values for all the lambdas. And then we see like the different approaches compared for 1,000 and 100,000 particles. The blue one is a brute force approach, as I said, using independent particle filters. And so this is kind of to benchmark the algorithm. And then we have the first version that eventually becomes zero, as we expected. In this case, there are more particles, so it doesn't go to zero yet, but we can see that it has more variance. And then we have the fixed lag approach and our adaptive approach, the Alvar, which is they are similar in terms of performance, but of course this lag, we've chosen here 14 and 24 because after trying many times, we thought that these were the best one, but we needed multiple runs, or just run the Alvar, take the average lag, and then run the fixed lag approach. But otherwise, there is no way to know it in advance. You have to make some trial and error. And also here, it's just a proof, and a simulation showing that with an increasing number of particles, the average lag selected by the algorithm grows logarithmically. So even with 1 million particles, then the lags chosen by the algorithm would range between, let's say, 15 and 60, so which is definitely manageable. Let's move to paper C. So the first one is on variational SMC, paper C. So it starts from the variational SMC concept introduced by these three concurrent papers that introduced, like, we define the law of a particle filter, and so the law of the particles and the indices of the particle filter, and then we define this lower bound to the log evidence by considering the expectation under this law of the logarithm of the product over time of the average of the weights, which is well known in SMC literature. This is a consistent estimator of the likelihood, and therefore, like, if this is a consistent estimator of this, then by Jensen's inequality we have this lower bound. And then they suggested that we can learn parameters and the parameters, like the model parameters, and also proposal parameters. So in this case, we assume that the proposal distribution depends also on the observations. Then we can, with this patch approach, like we assume that we have a fixed amount of observation up to a certain time t, and then we reprocess these observations multiple times and update with stochastic gradient ascent. So by simply computing the gradient of this elbow, this evidence lower bound. And in the paper also, they just write explicitly this gradient, and they claim that, and also with numerical evidence, that this additional term is not contributing and is only contributing with variance, but not with good, doesn't provide good contribution to the gradient. So they only use this as the gradient. And then we see that from this distributes over time, which means that we can create a Robbins-Monroe scheme. And this is our contribution on line variational sequential Monte Carlo by online updating the parameters of the proposal and of the model by simply taking the gradient of the log sum of the weights at each iterations. And here we see how we can learn parameters and also how the proposal that we learn tends to match the locally optimal proposal that we said at the beginning was, it's typically infeasible. I mean, it's not as of learning an optimal proposal. We don't know it in advance if you choose like a complex enough proposal distribution. And also we have also learned a generative model of a video. So the first line is the true video that we used to learn, and then the second one is to some samples from the after learning this generative model. I'll go a bit fast, sorry for that. And the last paper, recursive learning of asymptotic variational objectives, joint work with Jimmy again and Matthias, that is new PhD student. And our approach here starts from the recursive maximum likelihood approach, which aims, for the ones who don't know, to maximize an asymptotic objective, which is defined as the time average limit of the log likelihood or evidence. And then we instead create a lower bound to this objective using the principles of importance weighted autoencoder. Again, here we write this as an expectation, as a sum of expectations of bivariate variables that are sampled from the filter distribution and the proposal distribution. Here, for simplicity, we have theta parameterizing both, but it's more general than before. And then, so this is again, it's taken from the literature on importance weighted autoencoders. And using this objective, then we can improve the SMC, not in terms of like theoretical justification. So we can see here that if we want to take the gradient of, so we can create a Robbins-Monroe scheme here, because you can see that we have a time average, a sum over time. Our target function is at sum over time. So we can create this Robbins-Monroe scheme again. And then we have to just compute this gradient. And this gradient is an expectation with respect to, so this filter distribution times the proposal, but we don't know how to sample exactly from the filter distribution, but we know the particle filter, that is a way to sample from the filter distribution. But if we want to compute the gradient, we have to approximate integrals of this form, which involve the expectation with respect to a smoothing distribution, and here the product with an expectation with respect to the filter distribution times an expectation with respect to the smoothing distribution. But from our first paper, we can, and also previous literature, we can use algorithms to approximate smoothing distribution, like our AdaSmooth algorithm. And this allows us to create an algorithm that can approximate this gradient using SMC methods. So that is more theoretically justified because we don't have the truncation of the gradient that we had in OVSMC. And here we have some numerical simulations. So we are, to estimate the parameters, we are as good as the recursive maximum likelihood, but we are also better. We can see it here in terms of MSE. And why this? Because we are also learning the proposal. And by learning the proposal, we are able to generate samples that are closer to our target distribution and so reduce the variance of estimation. here are some references. And thank you for listening, and sorry if I've taken too much time.
All right, thank you very much. Let me welcome Stina back as well. Okay, thank you so much. We will now open up to questions from the audience as well. We also have a couple of questions that we have prepared for a short discussion. But my first question to the both of you is, how do you see your research, the research that you've done and so eloquently presented for us today, how do you see that impacting the statistical world? If we start with Stina.
Yeah, that's an excellent question, because we want to do research that is actually useful. And one way that I try to make my research relevant to applied researchers is by producing this software in this, for my PhD, it was this R package selection bias, so that if the applied researchers have a ready to use tool and hopefully user friendly, then hopefully that will lower the threshold for them to consider these methods. And even if they don't use them, it at least shows that they should consider these more advanced statistical concepts.
Mm. Excellent. And Alessandro, what's your?
Yes. So I think also I agree with Stina. I haven't published a package, but I try to also give let my code be available in especially for the last two projects, which also the computations are a bit coding is a bit more complicated, let's say, and technical. But I think it's a good question also, like to like go out and advertise it. I hope, for instance, that especially the variance estimation project would be used more, because I think it can make really like good impact on estimating, creating confidence bounds when doing inference in state space models, for instance. So I think I hope that this will be used more, and also really I hope that, for instance, for especially the last project that was completed maybe a bit quickly because I was finishing my thesis, to have some more numerical work on that, because I think I find it really interesting, and yeah.
Excellent. Out of curiosity, have you talked to anyone else who have used your research in their statistical work?
No, I think I had some contacts a couple of years ago regarding paper B of people that out of the blue contacted me also in another field, so they were very interested. But the problem there was that they were too applied, and it was a bit inaccessible for them. It was too much abstraction. But otherwise, I think other people that are closer in our community, I think they've used, and there was one professor was also interested in maybe include it in his own Python package that he has created, because he's also worked on similar problems. So yeah, okay. But I don't know how it went, honestly, now.
Stina?
Yes, not a lot, but I got an email a while back from a researcher looking at small businesses in Egypt and wanted to use one of the bounds. Unfortunately, in the end, I don't think they could use it, because they could not make this conditional independence assumption. And the assumption-free bounds were quite wide, because the selection probabilities tended to be quite small, and in the end it was not useful. But I think it was still good that they considered it, and they wanted to include something some kind of sensitivity analysis.
All right, excellent. And as you mentioned, Stina, you want to create research that is practically applicable. How do you see the scientific world and academia and the more practicing world of statistics moving closer and I mean learning not just from academia but also from each other? What are your thoughts on that, Stina?
That's a very good question as well. I think communication is quite important in these kinds of webinars, but also that now I lost the word. Sorry. That these applied work that who have the problems and they know all the details, that they can make them available to the researchers in some settings, and then also for the academia to include that, like if it is a methodological paper, to not just have a small toy example, but try to show how the method can be useful in an actual study, and not just a small simulated data set.
All right. And Alessandro, what are your thoughts on making the two worlds meet better?
Yes, I agree with what Stina was saying, and I think we need to make some steps toward each other, because some maybe also companies should also aim for maybe practitioners in terms. I imagine companies that maybe have also a bit bolder in terms of also starting something that might not work, because it's also a bit sometimes it can be a risk to just go into some new research that it has its own proof of concept, but then to scale it maybe can be more tricky and take some more time, and probably it's better just to stick to your own current method more safely. So I think it's a matter also of finding the right partnership in this, but but also maybe companies going. I think we had a course at KTH also. I mean, this is less related to research, but still, like companies instead showing what they are doing for their work, and maybe the learning from that and say, okay, but actually you could do this in another way, and then so I don't know. It's a bit of this and that, but I also think, because I come also from this more mathematical statistics aspect, it's also interesting sometimes to just do your own. I mean, of course, we need someone to fund us, but it's also nice to do some research that is out of interest itself, and not necessarily guided by certain logic. I think it's good for just creating knowledge per se sometimes, not all the time, but yeah.
All right. And on that topic, do you intend to continue your research, or do you want to go into more applied statistics? Alessandro first.
Okay, I actually now it seems that I'm contradicting myself, but I've left academia. I'm currently working at Scania, so still in data science, data engineering mostly. So, but it was mostly like a life choice, and I mean I preferred this choice, but I really enjoyed my time as a PhD student, and a few months after that just teaching, and also I like the academia, but I made this choice now.
All right. And Stina?
Yeah, so I'm doing a postdoc, not in selection bias and causal inference, so that research is put on the back burner. But I'm at the MRC Biostatistics unit at University of Cambridge, where I work on hypothesis testing for clinical trials that have a response adaptive design. So in these cases, the IID assumption is violated and traditional methods are not suitable sometimes. And my contract here is until July 2027, and it's quite a while. So we'll see what happens after that. But right now, I really enjoy academia and hope to stay here.
All right. Interesting to see different life choices. So the final question I have is, I mean, you've both worked with programming and R stacks, etc., but we're seeing more and more AI being introduced. How do you see AI impacting the work as statisticians? Who wants to go first? Let's go, Stina.
So I have not done any research in AI or machine learning. So for me, I use it as a tool, similar to other tools, and some parts of my work has been simplified quite a lot with using generative AI. So it's quite good for cleaning up code and translating code between different languages. So I had to translate some code from a colleague who uses Julia, and I use R, and that worked quite well because I didn't know Julia beforehand. However, I have tried to use it to write my own code, and that it did not work very well at all. So I think it can be very helpful if you have something that you know that you just want to change a little bit. It's also nice to use it for grammar checking and so on. But I haven't used it for any proper research, more as a help. Yeah.
And that is mostly because you don't find it reliable enough.
No, so for this example with the code, I tried to write a good prompt and then it looked very nice. But when I started going through it, it was basically nonsense throughout, and it was just deleting everything and doing it myself.
Right. Interesting.
Yeah.
Alessandro, what's your take on the AI debate?
Yes. So yeah, similarly, I also, I mean, I used it also for snippets of code. In that case, that's some like routine operations that maybe that helps, but still every time, I mean, I don't trust it too much. So always then after this, I Google the reference docs and all. But I don't know. I think it's difficult to make a forecast because I honestly I wouldn't have forecasted like what happens now with generative AI. I think when ChatGPT came out was a sudden thing, and in a few months it became so widespread. But I can maybe taking that perspective, I was thinking that probably there will be at some point, I don't know, some AI agents where we want to do some. I mean, this is okay. Maybe it's not related to the research part, more maybe to the practitioner. But let's say some practitioner wants to. I'm talking about my stuff. So let's say we have a time series and wants to do inference on this time series through time. So what and ask ChatGPT or similar some generative AI tool like, okay, what can I do with this data? How can I do it? And then I can imagine this agent suggesting different way of doing the analysis, maybe doing it, and I mean, which is already like that. But I would expect something more like with an agent that tells you like, okay, you have the option to use SMC, you have to use the option to use variational inference, but still, in the end, I still believe that the user has to validate it. I still don't trust it, but it's also a problem to educate people that use it to be skeptical. And but I think it's also tough because maybe they will become so good at some point that they will be also better at validating their own outputs than us. I don't know.
Yeah, it's a rapidly evolving world, but definitely interesting for sure. All right. With that, I thank the both of you very, very much for your very interesting and in-depth presentations and for the debate afterwards as well.
Thank you very much for organizing it.
Thank you. It's been a pleasure.
Thanks to all of you who have been listening in as well. And with that, I wish you a very pleasant evening and a Merry Christmas.
Thank you. Merry Christmas.
Bye. Merry Christmas.
Bye.